A very good morning, good afternoon, good evening to all the participants and the students for this multi-criteria decision making course which is under the NPTEL MOOC. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. And as you know, this course is for 12 weeks which is spread over 60 lectures, and each week we have 5 lectures, each lecture being for half an hour. And this is the 17th lecture out of the 60, that means we are in the 4th week. So, the overall so called superset or umbrella under which we are discussing the topics, we have been discussing under these topics many different subtopics. So, the topic was basically the simple definitions of MCDM, concepts of utility, safety first principle, stochastic dominance. So, obviously, definitions, concepts in details for utility theory, then the concept of expected value, certainty equivalent, then geometric methods, mean methods, then different type of utility functions, their absolute risk aversion, relative risk aversion using diagram as well as equation we have discussed with different examples. For the 17th lecture, and obviously it can go into the 18th also. So, we will discuss safety first principle, the concept of stochastic dominance, and also discuss the hyperbolic absolute risk aversion function and how hyperbolic absolute risk aversion function will make sense for all the 5 or 4 different simple examples of utility function we have taken, which was quadratic, exponential, then power and logarithmic. So, what is the concept of safety first principle? Under this basic tenet, the decision maker is unable or unwilling to consider the utility theory and the concepts for making her decision. So, he or she always wants to play safe and wants to minimize the risk or the loss, risk word I am using very generally, but the loss, but essentially not based on the concept of trying to make the use of utility theory. In utility theory, what we did? We always saw that we wanted to maximize the expected value, or given the fact if certainty values were known, we need to basically rank the certainty values. So, under this safety first principle, people make the decision placing more importance to bad outcomes. So, people are risk averse, so they want to avoid and they want to basically give more importance to bad outcomes, and based on that their main decision set of information would be. So, yes, this is placing more importance to bad outcomes, and we will see that in few minutes. Now, there are different concepts of safety first principle. So, we will consider 3 of them, and as given here the equations are given, I will draw them each one at a time in order to emphasize the fact. So, I will be coming back to this slide for 2 reasons, because the 3 main concept of safety first principle is there, and there is quite a lot of blank space where I can draw the diagrams and explain. So, consider for the time being the distribution is anything. Why I am talking a distribution? Because the decisions are random and there is a probability, and if you remember in utility theory, the concept of probability is used extensively, considering I want to find out the relative frequency of the occurrences of any decision which is being taken based on the wealth and its subsequent utility function. So, consider I will draw the x axis and y axis in black color. So, this is the x axis which is the random variable, and random variable what it is, I will come to that. This is the y axis, and the distribution for the random variable is this. It looks like normal, but it is not normal. I have drawn it very generally. Now, here what we mean by the random variable is basically the return. So, return can be total return, return can be rate of return. Total return mean capital R, rate of return being small r, and we have discussed what is capital R and small r. For just convenience, I will write it down and again erase it. So, I will use a different color red. So, if there are 2 values of investment, initial I1 final I2. That means, I invest I1 amount of money and at the end of the time period I get I2. So, I2 can be less than I1, can be equal to I1, can be more than I1. So, capital R would be equal to I2 by I1 and small r is equal to I2 minus I1 in the numerator divided by I1. So, the decisions which I am mentioning here, safety first principle, they do consider capital R, but they can be replaced with small r also. And if you remember, even though that is immediately not important for the discussion of safety principle, we also mentioned that if the distribution of the returns are normal, then the quadratic utility function would be utilized or vice versa. That means, it is both way implication if and only if. Now, coming back to the graph which was drawn. So, here along the x axis we would have the random variable which is the return, and for simplicity as the equations are given in capital R, I will denote R P, which is the portfolio or the conglomeration of assets which you have along the x axis, and along the y axis we have the PDF of R P, probability density function, and this value which I am marking with a star, the vertical line, consider for simplicity that it is the average value R P bar. It could be on the left, it could be on the right also, but for simplicity I am taking it. Say for example, R P bar, I will erase this line, could have been here average or could have been here, but the analysis of R P where it is placed, the diagram and its figure would make things much clear. So, I erase the x axis was deleted, I will again make it. Now, what we want to do and consider, there is a lower return RL. So, which is I am marking with a blue color, this is RL. So, RL consider is here. If it is on the right hand side of RP bar, I will denote that how it can be done. So, this is RL. So, what you would want to do is, in the case that I want to minimize the probability that RP is less than RL, RP not RP bar, which means I want to find out the overall area onto the left, I am marking with green. So, if RP is greater than RL, which is RL is basically the minimum requirement or threshold. So, if RP is greater than RL, it is better. If RP is less than RL, it is definitely not desired. So, I want to minimize the probability. In case RL was onto the right, the analysis also will be the same, consider RL is here. So, in this case I want to minimize the area onto the left. So, always concentrating on the left. So, in case if I denote that area with the hashed line here, so this would be violet area on hashed which I am denoting would be onto the left. So, I want to minimize this area. Consider RL is here on to the higher side of RP bar, and in this case I want to minimize for the green area, provided RL is onto the left of RP bar. So, considering that, I want to minimize the probability, which is the first bullet point, probability of RP being less than RL, and this would basically mean that I want to minimize, as I have told, either the green area or the violet area. Now, what advantage do we have with the normal distribution? Let us first discuss. So, I am only concentrating on the first part, first bullet point. So, if it is a normal distribution, I will draw it here. So, this is the normal distribution, this is the average, which is R p bar, and if R L is onto the left or to the right. So, this blue line is for R L. I am not marking the points R L on the left and the right, because it will become very cluttered. So, I want to minimize this area onto the left, or I want to minimize this area which is also onto the left. But in these two cases, the difference being R L is onto the left and other case R L being onto the right. Now, how do I utilize the normal distribution and the standard normal table? So, I will erase the diagram which was drawn with for any random distribution. Let us consider for the normal case, and I am going to basically erase this diagram in order to do the simple, not derivation, simple methodology of how you calculate. So, this normal distribution is now true, and I will write the equation. I will use the green color for this. So, what we have, if minimization of probability R p minus is less than R L, which would mean probability R p minus R p bar by sigma p. Sigma p is the standard deviation and R p bar is the average value, less than R L minus R p bar by sigma p, which implies probability of capital Z being less than equal to small z, and I need to find out. So, here from the data everything is known. R p is the normal distributed random variable, expected value is known, which I will put a tick mark in violet. So, R p bar is known, sigma p is known, I also put a tick mark, and R L is also known. So, based on that I find out the value or the probability, and using the standard normal table I can find out this value as alpha. And once I have different type of decisions with different alphas, I will rank them accordingly. So, I want to minimize, that means I will basically minimize all the values of alpha, consider alpha j, consider there are j number of investments or decisions, j is 1 to n, I will take the minimum one and take the best decision, because it is minimizing my area onto the left. Now, coming to the second bullet point, which is maximization of R L. So, I will continue the same diagram considering the normal distribution, even if it is the other the general distribution which I have drawn, the analysis remains same. So, I will basically erase this part. So, this was basically for the first bullet point. So, what we are doing is as follows diagrammatically. So, this diagram which is there, I will just try to expand it. So, it is not cluttered. So, this is the normal distribution which we have, this is the R p value, R p bar, and this what we are measuring is R p, and along y axis is the PDF of R p. So, what we want to ensure by the second bullet point is this is R L. Now, considering there are different distribution, I will try to push this R L onto the right hand side, which means that if I consider the concept of the first one, which was probability minimization onto the left. So, for all the distribution which were already given, considering their respective mean values, their respective standard deviation, if I push RL, so many of these distributions may slowly have their RP bar less than RL, provided RL is onto the left hand side. So, say for example, RL first instant I will put the suffix 1, this is not to the power, it is just a suffix to denote. Then it moves to the right. So, this is RL suffix 2, this is again not square, a suffix. Then it moves here, this is RL suffix 3. So, more I move to the right, I will be choosing that set of distribution where the probability of RL being greater than RP being greater than RL remains, which is in a sense that the probability onto the left hand side, which is for the case where I want to find out RL being less than RP being less than RL, continues to be minimum. So, because the probability is 1, so if I consider the minimization on the left hand side, which means what I am trying to consider the maximization on the right hand side, and if I push RL, so obviously the concept of minimization onto the left, maximization onto the right, both the ideas remain. So, I will maximize RL based on the fact I can increase to such level where I choose the best decision. So, the moment RP bar becomes less onto the left hand RL, the value of RL which is on the right hand side, many of these decisions would basically not be worth investing, because they would give a loss. And if you remember in the safety first principle, we did discuss that the decision maker pays more importance to bad outcomes. The last part is maximization of RP bar, and I will remove some of these here. So, RL is already here, RL 1, and what I am doing is this. I am trying to move the average value onto the right, which means lock stock barrel the distribution changes. So, if RP bar now moves to the right hand side, say for example, here. So, I will denote by RP 2 suffix, again not square, just a suffix, and this is consider RP 1, not a suffix, is not a power, just a suffix. So, in that case the distribution has moved to the right, which means it is like this now. So, technically if I consider the area onto the left of, because the chances of RP being onto the right as RP bar increases also increases, which technically means it fulfills the first norm. So, first norm and third norm and the second norm are interrelated. So, in this case I will maximize RP bar and then do the corresponding calculation. Now, the question may come up, so can we do it for any other distribution? Yes, we can, provided we can do the calculations to find out its mean RP bar, sigma p, and do the calculations either mathematically or simulation wise. Normal distribution has a table and is easy to do, hence I discussed those 2 examples. But remember that for the 3 cases which I had in front of me for the discussion, the first moment which is RP bar and sigma p should exist. So, if there is some distribution which does not have the variance, you cannot solve the problem, provided you are considering that distribution as being the case for the example to consider the safety first principle. So, the rule and discussion which I have written down in details, which I have diagrammatically explained, is exactly this. So, I want to find out Ri greater than Rf. Rf is basically the risk free interest rate which I was talking about, RL, the minimum some value. So, I want to basically, if I go here, it is exactly the same what we did in the last slide. I will write it down. It was Rp minus Rp bar divided by sigma p being greater than equal to. In the first case, it was minimization of less than equal to. Here, you will try to maximize the greater than. So, Rf minus Rp bar by sigma p. So, this one and the first of the safety first principle are the same. In the safety first principle, we needed to minimize because it was less than. In this case, which I have drawn diagrammatically, we need to maximize because either onto the left or to the right, the ideas would be same, but how you approach would be different. Minimization, maximization. Here, for the calculation which is shown here, the two important points which I have already mentioned. The second one which I will highlight is the returns are all normal, and I did answer that if the returns are non-normal, you can use it, but there were few important points which I mentioned. And RL is the risk free interest rate, which is the minimum case of RF. For the risk free interest rate, we took RL in the previous slide. Now, continuing the discussion of normally distributed returns, then in that case the optimum portfolio would be the one where RL was the maximum number of standard deviations away from the mean. Further, it is better because in that case the area onto the left is minimized. Let us consider an example. I have drawn and explained using the example for the normal case, and all the three safety principles were considered, but still let us continue further analysis of that. Let us consider an example for minimization of Rp less than RL, which is the first. Remember, we consider the returns are normal and the suffix p denotes the portfolio, while RL means a fixed level of return, which considered for our case as 5%, but I am using only the values. Now, consider the Rp value, Rp bar value is given, and you have for decision A as which I am putting a tick mark in red, the values of Rp are 10, for B which I am putting a tick mark in green, it is 14, and for C which I am putting tick mark in a violet is 17. The corresponding values of sigma p are, if I read the second row, it is 5, 4, 8, and if I consider the value of RL as given as 5, then the corresponding difference from 5%, which is the return, are correspondingly for A, B and C are given as minus 1 into sigma 1 standard deviation, 2.25 standard deviation and 1.5 standard deviation, which means that if I consider the distribution. So, let me make a blank slide and explain it, even though that is not part of the set of slides which will be uploaded, but I still want to discuss that. So, I will use the diagram data here and explain it. I will create a blank one. Yes. So, this is the slide just after this. So, I will keep switching between the blank slide where I will draw and this slide. So, consider Rp bar sigma p for A, B, C are given. So, let me draw it 10 and 5. So, values are, so let me write down the first the mean 10, 14, 17. So, if this is 10, so 11, 12, 13, 14, 15, 16, 17. And if I consider it's 5, 4. So, consider for the first one, consider 5 I am trying to draw as for the second one, it where the average is 14 is 4, it is 4, right. So, it will be a little bit more narrow. And for the average value being 17, its spread is 8. So, I will use a different color. So, this is the average value. I have tried to draw it, hope it's clear to all of you. Average value, average value. And what was RL? RL was here, was 5. So, it is 9, 8, 7, 6, 5. So, I denote the basis of RL here. So, if I consider the graphs going down, say for example, green is here, I should have extended it. So, what I want to do is this. For the red portion, if you see, I will use the red now pen, because I do not want to make it. For the red portion, I will minimize the whole area which is onto the left, for the whole red. Now, when I come to the blue one, which is for the second, yes, I will try to minimize this small area. Sorry if it is too minute, but this is the small area which I will have. And for the green portion, this will be that area corresponding under the green. For the blue, it was under the blue, for the red, it was under the red. So, if I zoom in this portion, if I zoom in, I would have this. So, this is RL. RL I should denote by, I will take few more minutes. This is RL. So, this I am considering zoom in part here. This is the left portion. The red distribution is coming like this, the green distribution is coming like this, blue distribution is coming like this somewhere. So, in the red case, I will minimize this on the left. For the green one, I will minimize this. For the blue one, I will minimize this. So, there are 3 ways. Idea remains same, minimizing this. So, with this I will end this class and we will continue discussing further on. Thank you very much.